So I have to start with an apology. So something computational which I was absolutely sure was going to give me no difficulty at all ruined my day. At the end it's working, but as a result I'm a bit less prepared on the theory. So my explanations might be lacking today. I'll do my best. Let me remind you where we were. So in principle, given some sort of an algebra, we are constructing a morphism from some sort of meta-algebra of tangles to the meta-algebra of powers of that original algebra. So basically here we have operations like Mij, so stitching component I to component j and calling the result component k, and inserting an empty component and various other operations. We went through it, and there are similar operations here, and we're trying to construct a morphism. To construct a morphism, we just need to know its values on the generators. And the first example was virtual tangles. And we actually had a running example, but it was a bit pathetic because it was running really slow. And well, okay. And then there is, for reasons that are unclear to me, there aren't many other examples. But once you kind of change the class, change what you think of it is important about knot theory, you get more examples. And then when I mean what you think is important in knot theory, when I say what I mean is, when I say what is important in knot theory, I mean which kind of local property of a planar knot do you retain? And then I mentioned last time that the thing that seems to be the most successful, and again, I cannot give you a reason why. It's just the way it is. And there are other things. And it's possible that the reason why this one is the most successful is because it's the one that's been the most studied. I don't know. Anyway, is rotational virtual tangles. So basically, this is, or what is it? What are rotational virtual tangles? So they are basically they're the result of the following abstraction process. So you look at the local structure of tangles and retain the graph theory, but also retain the rotation numbers of arcs in the plane. So, you know, if you draw the trefoil knot, for example, so here is one drawing of the trefoil knot, then some arcs kind of appear straight, and some arcs, like this one, does a 360 degrees rotation as it comes from here to here. So, so you have to keep rotation numbers, and I want to abstract that. Okay? So, okay, one way to do it is to say, well, so, you know, if I want rotation numbers to make sense, then the curves have to be smooth, and then the tangles shouldn't just have in and out points, but in these in and out points you should also be specifying an angle, so that when you connect one tangle to the next, the angles will match and the result will be smooth. Okay? Or at least C1, okay? But there is an easier way, and the easier way is to insist that all tangles, convention, all tangos at the ends are pointing up. So all tangos point up at ends. And then when you glue, it's clear how to glue. Right? You're gluing something that's pointing up to something else that's pointing up. It makes sense. So therefore, RV tangos will be the metamonoid, meaning I'm going to specify the generators, and then you will be able to relabel them as you please, and apply all those, the identity operators and the multiplication operators as you please. Sorry, the stitching operators as you please. So it's the metamonoid generated by an overcrossing. So strictly speaking, everything should be pointing up, so I should be writing it like this, right? Everything is vertical at the ends. But I'll allow myself to be loose, and if something is near vertical, you will know how to connect it to the vertical. Okay? So there is this generator with the usual, so in fact this is the inverse, so this is the negative crossing. So I'll call it R bar ij, where I is the label of the upper strand and j is the label of the lower strand. Second generator is the Rij with the same convention. And again, strictly speaking, things should be turning a little bit to make them going up. Okay? And then, and then there are the fun generators. So there is the generators, there are the generators that correspond to spinning around. Okay, to turning, so at the ends, things have to be vertical, but not along the way. Or at the ends, I want rotation, I want to make a rotation number to make sense, but things are allowed to rotate. If they were vertical all along, there would be nothing to talk about. So the other two generators are basically a lobe as on the left, which is called C, because it looks like the letter C. And when I say C, I mean it's C so that when you spin, it spins counterclockwise. And C bar, the inverse of C. Okay? So really I should have called it, I don't know, that, but that's actually a letter in the Hebrew alphabet, but not in the English alphabet, in as much as I know.
It's in the tree alphabet as
what?
well. In my language, we have the alphabet.
Oh, good. What is it called?
O.
O?
O, yeah.
Okay, I don't know. In Hebrew, it's called kaf.
Kaf.
So, whatever. But I'll just use C and C bar. Okay? So the generators are C on strand I. And C on strand I really looks like this. And it's spinning counterclockwise. So it's oriented, not as I wrote, it's oriented that way. And you see it's coming, it's starting going up and ending going up. Okay? And C bar, which is the opposite. Okay? But then I have to tell you what are the relations. Okay? So the relations are whatever relations will make whichever relations that if you impose them on planar things would produce ordinary tangle theory with all the ends pointing up. Okay? Basically, the relations so that I will include ordinary knot theory. So this is the kind of abstract, loose way of saying what are the relations. But now let's start enumerating them. Okay? So, you know, at the end I will enumerate Reidemeister 1, Reidemeister 2, and Reidemeister 3. But in a way, I should start, so somehow even more fundamental is the following weird relation. So the relation W, and W actually is not for weird, but for whirl. So you see, well, I suppose even before relations, I should have told you that these generators really generate. Okay? So why do they generate? So give me a note. It's not clear that all crossings have their strands pointing up. Okay? But what is clear is that if you have a crossing somewhere and it's not pointing up, you can hold it with your hand and rotate it by 180 degrees. Okay? And then it will be pointing up, but you will be introducing some whirl around it. Okay? But you don't know, I mean, but you know, you can twist this way or twist that way. Or said differently, if you twist 360 degrees, you should be doing nothing. So the whirl relation says that if you have a crossing and you fully spin it around, and this is hell to draw, so you fully spin it around, so it's hell to draw because at some point you need very slow, high resolution lines. So this is equal to that. Okay? It's slightly more convenient to draw it as follows. So basically, sorry. It's slightly more convenient to draw it as follows. So basically, oh sorry, and all the orientations here are up. So basically, if you go from here to here, what you see is, I think the letter C, no, this is a C bar. So if you go from here to here, you see a C bar. But it's easier to draw it this way. So let me put a spin going wait, I want to go clockwise, right? So, sorry. So it's easier to draw it this way. So this is just a notation for make a 360-degree turn. And this way, and that way, and that way, I think. I hope I didn't mess the orientations. Sorry. Okay. Yeah, it's right. Okay, yeah, sure. Basically, if the crossing wasn't here, this should cancel that. So it should be a rotation in the opposite direction, and that's already. Okay, so that's the first relation. And then I should be writing all the ordinary relations of knot theory. So the ordinary relations of knot theory. So I mean, after I've made all the things point up, I should still impose the relations of knot theory. And they are, so let's see, Reidemeister 1, which you may or may not include, sometimes you don't. But let me emphasize that Reidemeister 1 is now a product of two generators. So what's Reidemeister 1? you take a crossing and you connect this end to that end, and then you're supposed to get the nothing. So this relation is really a C times an R. So schematically, this is C times R is equal to 1, but you have to be careful about what exactly gets stitched to what. Okay, but schematically, it's C times R. And in fact, there are 4 variants because well, this crossing could be flipped, and then it will be C times R bar, or the king could be on the other side. So you could have a picture like this, and then this will be a C bar times R is equal to 1. So, but this is again schematic. Okay. Then there are 2 types of Reidemeister 2. So there is the easy Reidemeister 2, which says that if you have 2 crossings, well, basically, the easy Reidemeister 2, which is called Reidemeister 2b, so where the things are like, where the strands are braid-like, everything is putting in the, pointing in the same direction. And then this is just a relation of the form R times R bar is equal to 1. And then there is the weird Reidemeister 2. So the weird Reidemeister 2 at first appear to be not in our language. Wait, no, I think I want to write it the other way. So it doesn't matter. But so at first it appears to be not in our language, right? I don't know how to impose this relation, because okay, so this is the relation in which there is the bigone in the middle is cyclically oriented, and it appears to be not in our language because the vertices are because the crossings are not oriented up. Okay, so how do you write it in our language? You do exactly what I said you do. You whirl it in the right way. Okay, so let me just write what it comes out to be. So it comes out to be the following. So R2 cyclic comes out to be the following relation. So if you have a single strand here and a picture like this, so I think I wrote the orientation right, then it's equal to a picture, wait, no, sorry, I wrote it now with the Hebrew alphabet. I meant to write it with the English alphabet, sorry. So if you have a thing like this, no, God, I want to write the letter C. What does the letter C look like? Like that. Right, yeah, okay, sorry. I'm sorry. But it's oriented this way. Yeah. So this should be equal to that. Wait, is this C? Yes. Sorry. So, again, as a Reidemeister move, it's a Reidemeister move between, well, it's a Reidemeister move in which the orientation inside is in which the bigone is cyclic. But all the generators are written with things pointing up, except that there is an extra generator. There is a C here and a C here. And schematically, this relation is of the form C R bar is equal to C. Or, you know, if I wanted to even be kind of truer to the original, it's R C R bar is equal to C. Though you have to be careful about what gets stitched to what. Okay? And I think this will all be clearer once I write an implementation, because then I'll be forced to actually write the formulas and they'll stop being schematic and become precise. Okay? So to have an implementation, I need to have an example. And the example is the so-called, well, okay. So the example is an algebra which I will call the Kerler Algebra, named after Thomas Kerler of the University of Ohio, though I have to admit that it's a bit improvised, sorry. Namely, I read his paper and got inspired by it, but I'm not sure that it's actually the same algebra. Okay? So I'll call it the Curler Algebra K, but I'm not promising that it really is the Curler Algebra. Anyway, what's the Curler Algebra K? It's the algebra with 5 generators and some relations, A, B, C, D, and K, lowercase k. In this case, you know, the Kerler element, I don't know, Kerler. Modular relations. I have to tell you what are the relations. So here are two ways to write the relations. So one way is, so really, let's first talk about A, B, C, and D. So A, B, C, and D are organized like in the 2x2 matrix A, B, C, D. So more precisely, A is the matrix. So A is the matrix 1, 0, 0, 0, 0. B is the matrix 0, 1, 0, 0, etc. And then the relations are that they multiply like matrices. Okay? Here's a different way of saying the same thing. So you draw the following graph. So you have two nodes, and basically you write this graph, and then A goes from this node to itself, B goes from the node 0 to node 1, C goes from node 1 to node 0, and D goes from node 1 to node 1, and they multiply by kind of concatenation, and if they don't match, the product is 0. So in other words, A times B, so if you do A and then B, you went from 0 to 1, so it's B. So A times B is equal to B. B times C is equal to A. BC is equal to A, and so on. But if you try to multiply A and then D, so if you try to multiply things where the ends is not equal to the beginning, like matrix multiplication, you get 0. So that deals with the relations between A, B, C, and D. And then K has two properties. So K squared is equal to 1. And so K is, so in fact, what we're doing is we're taking the semi-direct product of the algebra of 2x2 matrices with a Z mod 2. The Z mod 2 is this K. So, and K, when conjugating A, B, C, or D, so K inverse A K is equal to roughly A. K, but you see, I don't need to write the inverse because K squared is equal to 1. So likewise, KBK is equal to roughly B. KCK is equal to roughly C, and KDK is equal to roughly D. And I said roughly every time. So roughly means plus or minus. And the rule is that if the element cross, if an element cross this white line between the two blackboards, so if an element crosses this middle line, then K anti-commutes with it. So KBK is negative B, KCK is negative C, and KAK is plus A, and KDK is plus D. Now I've fully specified the algebra. So so let me be a bit more precise about this algebra. So the algebra is really, so as an algebra it's generated by 4 things. As a vector space, it's generated by 8 things. So as a vector space, it is generated by, so you see, if an expression has only A, B, C, and D's, I can multiply them as matrices and get one of A, B, C, and D. So I just need one of A, B, or C, and D. So, so it's A, B, it's C, and D. And then, if an expression also has a K, I can move all the K's to the left, basically using this relation. So I can move all the K, I can move a K all the way to the left, and every time I cross it with a B or a C, I get a negative sign. And when I cross it over an A or a D, the sign doesn't change. So I can move all the K to the left. If there is another K, I can move it to the left too. So I can bring all the K's to the left. But K squared is equal to 1, so there is only one K. So there is either 0 K's on the left at the end or 1 K. So the further generators are KA, KB, KC, and KD. So it's an 8-dimensional algebra. Okay? And I want to show you an implementation of this algebra. And then, so the order is, I'll implement the algebra, and then I'll go back to knot theory. Okay? So, the implementation of the algebra is rather trivial, is rather easy. So, you know what, let me execute the first line, even though it's still just about knot theory. I don't need it for the algebra. So I'll execute the first line, and then the implementation of the algebra is fully on the screen. All of it is on the screen right now. So first of all, I typed in by hand a matrix called MT, and MT stands for multiplication table. So basically, if you look at, gee, I can't, it's too far. So I don't know, if you want to know what is B times C, you look at B times C and the result is A. Because indeed, B followed by C is A. And then, you know, K times anything, so Ka, Kb, or Kc, or Kd, with Ka, Kb, well, sorry, K, a K thing with a non-K thing gives you Ks. A non-K with a K gives you also Ks, but sometimes with signs because you have to move the K to the left. And a K thing times another K thing gives you a non-K output, but again with signs depending on how many times you have to move a K across a B or a C. That's the multiplication table. It's a 9 by 9 matrix because it has an extra column for the names of the rows and an extra row for the names of the columns. And then I tell you what to do if you have an expression and you want to multiply tensor factor I with tensor factor j to get output in tensor factor k. So I work with my usual conventions. which is that I indicate tensor factors with subscripts. So basically, if I write A1 KD2, then other people would write it as A tensor KD, and it lives in the Kerler Algebra square. Right? So now I need to tell you what is any subscript. So basically, for each of the 64 possibilities of something in I and something in J, so the something can be any one of the 8 generators, I need to tell you what's the output. So I generate a table in which I look at the alpha 1 entry of the multiplication table. So basically I'm looking at the column, and then the 1 beta entry of the multiplication table. So I'm looking at the row label, and then the rule is whenever you see a product like this, you replace it by whatever is written in the multiplication table in position alpha beta, except if it's either any one of the generators, you add a subscript k. So, this might be a bit abstract. So perhaps I should simply generate this table, just for once, to see what it looks like. So, oops. Oh, I forgot to input the multiplication table. So here's the table. When you're multiplying ij and the output is to be k, then if you have a kc in position I and an aj in position, a kc in position I and an a in position j, the output is kc, and so on. So that's just the, so multiplication just works by applying this rule to whatever input expression you had. So that's a part of the structure. This is the multiplication part, the hard part. And then I also have to tell you what is eta. So actually this is an algebra with a unit, but I forgot to tell you what is the unit. The unit is the identity matrix. The identity matrix is none of these generators. The identity matrix is A plus D. Right? So the unit is eta I, and it's AI plus DI. And then, I want to check associativity and all that. And for this, I need to know the basis. So basically, the basis of k at one factor, tensor factor called I, is just the 8 generators. And if you want the basis with several tensor factors, then you basically take the Cartesian product, that's this outer product here. So the Cartesian product of the basis in position of tensor factor I with the basis in the rest. So once I've executed this, I have basis. So like if I look at k basis of 1, it will be just that. And if I look at k basis of 5 and 6, so it's all the possibilities of putting, well, basically it's the 64 elements that you get by taking the 8 generators and putting one in position 5 and one in position 6. And now I need to check associativity. So I look at the basis with 3 tensor factors. That's actually pretty big, right? That's 512 elements, 8 cubed. And then I multiply in one order, and then this is the left-hand side, and then the right-hand side is the same thing multiplied in the other order, and then I compare left-hand side with right-hand side, and my syntax was such that, so I display the first product in short form, because otherwise I'll get 512 things and it will scroll too far. The second, the computation of right-hand side ends with a semicolon, so nothing is printed, and then LHS equals to RHS gets printed. So hopefully it will print true. If it doesn't print true, this isn't an associative algebra. So it did print LHS in short form, 502 things are missing, and it printed true. And then likewise, we can check whether you have units. So whether the units are units. So eta 1 multiplied by anything in the basis in position 2, and multiplying 1 and 2 to get 1 should give just the basis in position 1. And similarly for the other direction. And again, oh, why did it say true? Okay, it says true, but I thought, oh, wait, I was going to hide all the output, but I forgot to do it. So now I'm hiding it back again. But now I've hidden also the stuff that I was supposed to show. So let me re-execute everything. Sorry about that. Okay. Well, but you see, it's not enough to have an algebra, right? I also need the R element and the C element. And here they are. I have nothing good to say about them. So really you should be asking, and where did they come from? Okay, how would one ever discover such a thing? Okay, and I think I want to comment on that later. At the moment I want to just say, here it is, okay? And let's verify that it works. So Rij is R. So in fact, it's not just, there isn't just a single R. There is a one parameter family of R's, depending on a constant T. Likewise, there is a one parameter, so basically there is a one parameter family of Kerler algebras. And therefore, the invariant you will get will depend on a parameter. It will not just be a number or an element of the algebra. It will also depend on a parameter. So in fact, it has a chance to be a polynomial, a Laurent polynomial perhaps, because some inverses appear here, and it will be. Okay? But anyway, I really have nothing good to say about these elements. So Rij is given by this ugly formula here. R bar ij is given by that ugly formula. And what I really need to do is to check, is to verify all the axioms. So let's go through the non-interesting ones quickly and through the interesting ones more slowly. So Reidemeister 3 is actually not interesting because it's identical to Reidemeister 3 in situations we've seen before. So you multiply 3 R matrices and you contract the tensor factors or stitch the tensor factors in the right way and in two different ways, and hopefully you get an equality, and you do. No, I forgot to execute this. Sorry. So now you do. Likewise for the braid-like Reidemeister 2, which is essentially asking whether whether R is the inverse of R bar. Yes?
So for Reidemeister 3, there are also multiple Reidemeister 3s that we would actually have to check.
Yeah, but they follow from, so in principle you're right, but they all follow from the Reidemeister 2s. And so if you know all, so these are the only relations you actually have to check because the others follow. Okay? So likewise, Reidemeister 2b is not interesting, and it comes out true. But then the naive Reidemeister 2c. So let's try to understand what's written here, the thing called naive. Okay, here. So what am I doing here? I'm multiplying two R matrices, 1, 2, and 3, 4, and I'm multiplying them in a certain order. So let's see what it looks like. So it's really, okay. 1 is above 2 in a positive crossing. Sorry, so it's actually, sorry. So 1 is above 2 in a positive crossing. So okay, so 1 and 2, and it's supposed to be a positive crossing, so it's oriented like this. Yes. And then 3 is above 4 in a negative crossing. So 3 is above 4, and this is a negative crossing. And I am stitching 1 to 3 and 4 to 2. So,
because that's a positive crossing, right?
What?
It's a positive crossing. The 3, 4.
Oh, sorry, it's the wrong crossing, you're right. No, but I also, oh, sorry. It's 1 to 2, maybe it's better if I'll draw it above, it will be easier to stitch. So 1 to 2, okay, so 3, so 3 and 4. So I'm stitching 1 to 3, calling the output 1, and 4 to 2, calling the output 2. So basically I'm stitching this way, right? And this should be equal to, well, this is just a Reidemeister 2, so it should be equal to that, namely this. But, you know, after stitching, I'm calling 4, 2, 2. And the 1, 3 strand, I'm calling 1. So it should be eta 1, eta 2. So I'm checking this. I'm computing the left-hand side. I'm computing the right-hand side, eta 1, eta 2. And, sorry, it's down here, naive Reidemeister 2. I'm computing the left-hand side, I'm computing the right-hand side, and I'm simplifying their difference. And, well, you get this, and this isn't 0, right? So we failed, okay? But we failed because we were doing the naive Reidemeister 2. So now let's do the correct Reidemeister 2. And the correct Reidemeister 2 is written over there. So I hope I'll do it right now. So really it's this picture. So, no, yes, it's this picture. So let's call the elements, or let's label the strand. So now everything is pointing up. And let's call the strand. So basically the C strand. So the C strand is, say, from here to here. So this is tensor factor 3. This is tensor factor 1. This is tensor factor 5. This is tensor factor 2, and this is tensor factor 4. So what I have here is a C3. Here is the C3. A crossing between 1 and 4, a positive crossing between 1 and 4. It's the opposite orientation. So it's a positive crossing between 1 and 4. I'm sorry, I blundered orientations. Modulo blundering the orientations. No, it's actually wrong as written. It should have been a C bar. So if I do the orientations right, it's a picture that looks like this. C bar. So it's a picture that looks like this, right? So 1, 3, 5, 2, 4. So 1 over 4 with a positive crossing, but then it's a C bar. So what I wrote here was actually wrong. So let's add bar everywhere. So I'm adding a bar here, and I should be adding a bar on the other side of the equation. And let's test it, and it still came out true, so I was lucky. Okay? Then, in fact, I should have checked even earlier that C and C bar are inverses. Let's check it. What did I do? Here. Well, the output, I didn't check what it's equal to. I just multiplied the product, and this is indeed identity. Then there are 4 Reidemeister 1s, so each one is made of a C and an R, or a C bar and an R bar. So I check all of them, and they're true. And finally, there is the whirl. So the whirl is, where did we write it? Here. So it's basically a C bar, an R, a C, and a C stitched together, and the output should be a single R. So I'm checking if, well, this is the left-hand side, the right-hand side is a single R. I hope I made no mistakes, but the computer approves. I'm sorry, I warned you this, I was a bit fuzzy today. Then comes a surprisingly hard part, which is, well, so now we actually need to compute the invariant, right, to see whether it's interesting or not. And whether it's, how quickly it computes, right? And there is a technical difficulty. And the technical difficulty is, so notes, the way notes are given in our standard notation, so like if I write note 817 and try to find its PD, then it's just a list of crossings with no rotation numbers. And I have to, from the list of crossings, so I know that these crossings can be placed in the plane in only one way. But I still don't know, so I should be able to recover the rotation numbers, at least up to whirls. But I haven't, but that's actually a hard challenge. So we'll have to do it next time, but it's actually very complicated. And so we'll have to do it next time and then execute it and eventually see whether we can actually compute what we want or not. Okay? And so yes, so I'll continue next time. And I'm you know, no, so sorry. Part of math is hard work. I don't know what to say. So, okay, see you next time. See you on Friday.